All right, last functional group of the chapter. This chapter is a long one, so it feels good. So last one is epoxides. Which of these is an epoxide? Hopefully you remember that from the beginning of the chapter. That one. So epoxides are essentially ethers that are shoved into these ring systems. So which molecule would be more reactive? This one here or this one here? You've thought about it, you paused the video, but also write down why you think it's more reactive if you have an idea here. You should be able to put some words to this. Great, you did that. So B is more reactive. Why was that? Well, it has that angle strain. What was that angle strain? Well, this is a little triangle, right? The interior angles of that triangle are around 60 degrees. This angle right here would be 60 degrees. Is that going to be a good thing? Well, no, right? What's the hybridization of this carbon? This is a CH2. That means it's a carbon with 4 things attached to it, which means that it's sp3 hybridized. And if you're sp3 hybridized, you want to be tetrahedral. You want to have 109.5 degree angles. Or approximately that, right? Not necessarily perfectly 109.5, but something close to that. And we're 60, so we're very far apart from that. So lots of ring strain, lots of angle strain here. So that makes that molecule a lot more reactive than your standard ether. And really, it turns out that epoxides kind of break a lot of the rules that we've heard about for oxygen-type functional groups. So what do I mean by that? Well, if we take this ether right there and we add a strong nucleophile to that, or really any nucleophile, what's going to happen? Well, we've talked this whole chapter about O- is not a good leaving group. So if this nucleophile added to there and kicked off O-, we would have O- plus nucleophile that's attached to a carbon, right? But it turns out that this reaction doesn't happen. These things are not formed because this is a poor leaving group. So what about epoxides? What's new here? Well, because of all this ring strain, all this pent-up rage in this small, strained ring, this thing's really reactive. Pent-up rage. It does not want to be like that. So it turns out that, sure, an O- is usually not a good leaving group, but when you have all this energy and small structure, it just wants to open up. So the nucleophile will add to it, just like it theoretically, like we're drawing the arrows here, the nucleophile is negatively charged. This would be partially positive, but because that's a poor leaving group, it won't happen. This also has that big partial positive on it, but this one will happen because that product is no longer cyclic. We have our acyclic product, so we have the ring strain relieved. Ring strain relieved. So epoxides break our normal rules because although O- is usually not a good leaving group, it is a fine leaving group when it can provide a open structure from that really strained system. So what's the blank in here? Epoxide ring openings occur through an SN2 type mechanism. So the nucleophile added while that carbon-oxygen bond broke simultaneously. Now we're going to talk about strong versus weak nucleophiles and their ability to open up these epoxides. Yeah. All right, so different types of nucleophiles will add to epoxides in different types of ways. So it turns out that strong nucleophiles can open neutral epoxides, so epoxides that have no charge on them. But we have to ask ourselves, well, This is an epoxide carbon-oxygen bond. This is an epoxide carbon-oxygen bond. Which side is the nucleophile going to add to? So to think more about that, we know negatives flow to positives, but as far as that doesn't really help us too much. We might have a negatively charged nucleophile like this methoxide here, but there's probably a partial positive there and a partial positive there, right? Because this oxygen is going to be pulling away from both of those positions in a pretty similar way. The second rule of organic chemistry, though, is the ball rolls downhill. So we're going to break the bond that is weakest. We're always picking on that weak bond. So that epoxide right there has been generated computationally. I have that right here. And essentially, what we see is that the bond lengths are of really similar length. Yeah. So we have 1.435 angstroms and 1.433 angstroms. So essentially, each CO bond in the neutral epoxide is a similar length. We just saw that. And how did length relate to strength? We know that, right? So yeah, they're similar length, which means they're similar strength. So they're similar strength in a neutral epoxide. We'll write length too, just to put that in there. Length, because that's how those two things relate. A shorter bond is a stronger bond generally. Therefore, the nucleophile adds at the more blank carbon atom. So I want you guys to think about that for a minute. They're the same bond strengths, so do you think that the nucleophile is going to add to carbon A, as I've indicated, or carbon B there? So pause the video, make your selection, and give yourself a little rationale for why that is. Good job, you did it. So what's different about these two positions? If we had to go through our standard, like, what type of chemistry is going to happen here? We have a strong nucleophile. That means we're going to be doing a bimolecular type process. The next thing we look at is the substitution of the electrophile. This would be kind of a primary leaving group from carbon B. So we'll write primary on this side. This would be more of a secondary leaving group because this is a carbon attached to two carbons. What are we going to put in this blank up here? Really what I'm looking for is the nucleophile adds to the more kind of open carbon atom, the more accessible carbon atom, the one that isn't blocked, right? Because it has to add to that antibonding orbital. So the more, we'll write more accessible carbon atom. So what do I mean by that? Well, this carbon atom here has an H and then it has a big CH3 group. This one has an H and another H. That CH3 is a lot bigger than a single H, so this is the more accessible carbon atom. So how do strong nucleophiles react with these neutral epoxides? The nucleophile, the OCH3 minus, is going to add to the more open position and pop open that ring. So after we've added reagent 1, we would have a structure that looked like this. And then what is the ultimate product after we add reagent 2? Here. We just have a basic oxygen here. We have hydronium ion, an acidic, a source of H+. So that would just grab that proton. Might as well draw it in. Gone through all that work already. So that would generate our neutral organic molecule here. Did anything change with our stereochemistry at this position? No, nothing happened to that carbon. If nothing happened to that carbon, it's going to stay the same configuration. So make sure you're not switching that wedge to a dash or a dash to a wedge, etc., etc. Great, so that is how strong nucleophiles open these neutral epoxides. Great. All right, so strong epoxides, or strong nucleophiles do one thing with epoxides, weak nucleophiles are a little bit different, right? So if we had a weak nucleophile just by itself, like Cl minus, this is just too weak. This nucleophile, this epoxide's like, yeah, I'm really strained, but you are just too weak to open me up. So essentially, weak nucleophile like Cl minus and that, we're just going to have no reaction. So that's the first thing that we have to think about is if the nucleophile is too weak, it's just not going to react. But if we, and that kind of fits the same situation with an alcohol, right? If we had an alcohol and we were trying to react with Cl minus, nothing's going to happen. So how did we make the alcohol react and substitute with Cl minus? Well, we protonated that alcohol to make it a better leaving group. And that's the same thing we're going to do here with an epoxide if we want the reaction to, if we want that weak nucleophile to still be able to substitute. Instead of using sodium chloride, we're going to use HCl. So how is that going to work? Well, just like all the other oxygens that we've dealt with, if we have an oxygen and a strong acid around, the first thing that's going to happen is we're going to get proton transfer to that oxygen. So that's going to give us our OH plus. And now it's really important to think about, well, what did we do last time? We wanted to break the weakest bond, and the bonds were really similar in strength. So we went for the one that was just more open. But now we're actually in a little bit of a different scenario. We have a protonated epoxide, so again, we have to kind of look at the bond lengths. And when we do that computationally, what you see is that the bond to the more substituted position, so this is the more substituted position, is 1.59 angstroms, and the other one is 1.51 angstroms. So the bond to the more substituted position is a longer bond and a weaker bond. So protonation of the epoxide weakens the CO bonds asymmetrically, making the CO bond to the more substituted carbon longer and weaker. Which again, if it's weaker, you could write here as well, more reactive, right? So if we really wanted to depict this in reality, we'd do something like this, where we would show a really long bond to the O from there. And why might that be like that? Well, this oxygen does not want to have a positive charge. It is pulling electron density away from that carbon, and essentially it's trying to, these carbons are trying to even lend it a little bit of their electron density, because a carbon would rather be positive than an oxygen. So they're actually going to take on some partial positive character themselves. So the next question becomes, if we have a partial positive here and a partial positive here, which position is better at stabilizing that partial positive charge? Yeah, more substituted positive charge is a more stable positive charge. So we probably have a pretty big partial positive charge there and a much smaller partial positive there. Again, backing up this whole bond length issue. The longer bond is the weaker bond. So it turns out that when we have a weak nucleophile like Cl minus, we have to catalyze it with acid first of all. But that Cl minus is going to add to the more substituted position, because that is the carbon-oxygen weaker bond and the larger partial positive. So that Cl minus is actually going to add right there, opening up that carbon-oxygen bond. What does this look like? Well, the product then will have the chlorine at that position. The OH is up here, and the CH3 is right there. Did that stereocenter invert? Yes, it did. If you look RS at this one, this is priority 1, priority 2, priority 3, but it's in the back, so this is S. And if we look at this one over here, priority 1, priority 2, priority 3. This one is R, because that thing's in the back again. So we went from S to R. Also, if we rotate around this, so we're rotating around this bond right here, I'm just going to redraw the molecule. And you should do this yourselves to make sure you're getting this. These two are the same molecule. These two are the same molecule. And again, this would be the first priority, second priority, third priority. This would be R. So what am I getting at here? Well, when the nucleophile adds to the more substituted position, that position is stereogenic. So an SN2 reaction at the more substituted position inverts that stereocenter. If it was S, it's R, vice versa. So last blank on here was the nucleophile adds to the carbon that is more stable with a partially positive charge. So that's the carbon that's more stable with a partially positive charge. And again, that was right here on the course packet. So now we're going to do some predict the products with these epoxides. Okay.